Okay, so let's have a look at a worked example of how to apply propagation of variances to multiple derived quantities. So in this particular example, we are going to look at deriving internal angles from total station or observed directions. So in this case, we're going to compute three internal angles from um, four observed directions. And our task is to compute the internal angles and then to compute their standard deviations. Okay, so let's look at the actual example here. So we have four observed directions listed in the table here. Here they are, direction 1, 2, 3, 4, and we have their standard deviations in seconds. The measurements themselves are in degrees. We are going to compute the three internal angles shown in the diagram on the left. So the first thing we are going to need to do is establish, first of all, what it is we're computing, what it is we've measured, and the relationship between them. And we need to get that into the form that we're used to or that we know how to use with our propagation of variances, which looks like this. In this case, the values that we're computing are the internal angles. So we'll put those into a little vector here. And what we're computing them from are our directions. So let's put those over here. And we'll need the relationship between them, which will be our A matrix. Okay, so alpha 1, according to the diagram, is calculated as direction 2 minus direction 1. So we will put a minus 1 in here for the direction 1, a 1 for the direction 2, and zeros for direction 3 and direction 4, because we are not interested in them. Our second angle, internal angle, alpha 2, is, according to the diagram, computed as the difference between direction 3 and direction 1. So again, we would have a minus 1 here for direction 1, no direction 2, 1 direction 3, and no direction 4. And our final internal angle, alpha 3, is computed as the difference between direction 4 and direction 1. So again, we would have negative 1 direction 1s, no direction 2s, no direction 3s, and 1 direction 4. So we have our linear relationship here set up. And so we have one other thing to do, which is to construct our variance covariance matrix for the measurements. So let's do that over here on the right. Now there are four directions. So our variance covariance matrix would be a 4x4 matrix here. And of course, down the diagonal, we'll have the variances. So here's the variance of direction 1, the variance of direction 2, the variance of direction 3, and we'll need to redo that. Ran out of room. Now the directions are all independent of each other, so they don't influence each other, they're uncorrelated, so everything in the off diagonals here will be zeros. And of course it's symmetric, so these are all zeros up here as well. So we'd only have terms down the diagonal. Okay, so now that we have our setup here, let's put this into Microsoft Excel to do some calculations with. Okay, so we'll put our Y matrix in first here. So that's alpha 1, alpha 2, alpha 3. And we needed to compute those from our A matrix, which we had as being -1, 1, 0, 0, -1, -1, 0, 1, 0, and 0, 0, 1. And we also had our X, which was D1, D2, D3, D4. Okay, so you could substitute numbers in here. So D1, 15.75, D2, 12.00, 65.5, and what are we at, 96.25. Now you could manually work out these values here, alpha 1, alpha 2, alpha 3. So let's just do that quickly for the first one as a bit of a check, and then we'll do it via matrix algebra. So this should be the difference between D2 and D1. So we'd be expecting this, and I've typed that in wrong. That's 32, not 12. We were expecting this to be the difference between direction 2 and direction 1. So this should be 16.25 degrees, which is the difference between these two. So let's do that via matrix algebra in Excel. So we'll delete these. This will be matrix multiplication of A by X. And of course, Control Shift Enter to get the values. Okay, so we've answered the first part that we were required to do here. So that simple calculation has allowed us to answer A. We've calculated the internal angles here. Now we need to move on to the bit that uses propagation of variances, part B, the standard deviations of the internal angles. We have the internal angles here. Okay, so in order to do propagation of variances, we also need to set up the variance covariance matrix of X. So let's go ahead and do that. Now we know from the setup here that down the diagonal we will have the variances of the various directions. What we have in the table here are the standard deviations. So the standard deviation of direction 1 is 6.5. So its variance will be 6.5 squared. the variance of D2 will be its standard deviation, 8.5 seconds squared. And so on for the last two, 5 and 7.5 respectively. And based on our setup, we said all the measurements, all the directions were independent, so they're all zeros for the off-diagonal terms. Okay, so now we have that matrix set up. We can apply the propagation of variances. So we know from equation 5.1 that propagation of variances, if we want to know the variance matrix of y, which is what we're after now, propagation of variances tells us this. So let's implement that now. Now we have three internal angles, so our variance covariance matrix for our internal angles will be 3 by 3, and it is the matrix multiple of our A with the matrix multiple of Vx with the transpose of A. Close off all your brackets there and Control-Shift-Enter to fill up your matrix. Oh, we must have an error somewhere. I've missed a bracket. Let's fix that for me. I needed a third bracket on the end. Okay, so this variance covariance matrix consists of the variance of alpha 1, the first internal angle, the variance of alpha 2, which is our second internal angle, and the variance of alpha 3, our third one. But you'll also notice that these angles are correlated, and this makes perfect sense when we go back to the diagram. So obviously alpha 1 and alpha 2 are correlated because they share a common direction here. So if something happened to this direction and its precision, that would impact both alpha 1 and alpha 2. So alpha 1 and alpha 2 are correlated because they share D2. So it's not unusual for these correlations to be here. We're expecting them. You'll also notice that the matrix is, as predicted, symmetric. Okay, so the question we were asked is actually to provide the standard deviations of the internal angles. So we don't have that yet. In order to calculate the standard deviations of alpha 1, alpha 2, and alpha 3, we need to take the square root of the diagonal elements here. So we can do that again using Excel. And these are in seconds. Just tidy them up a little bit, make them a bit easier to read. And so now we have answered part B. We now have the standard deviations, precisions if you like, of our computed angles. So we computed the angles up here, and then we have their standard deviations here as asked. So that's a worked example of using propagation of variances with multiple derived quantities.